The next question is, for ketones, the more intense band near 180 nanometer is due to. In the case of ketones, there are two bands. One is intense at 180. One is intense at 180. Another is at around 275. It is less intense than this. This is weaker than this. So 180, that is the intense band at 180, is due to pi to pi star transition. So due to the pi to pi star transition, we'll get the intense band at 180 nanometer, and due to n to pi star transition, there will be a less intense band, weak band at 275 nanometer. Hence here they have asked the 180 nanometer intense band at 180 nanometer. This is due to the pi to pi star transition. Next question is, the number of translational, rotational and vibrational degrees of freedom of CO2 are. The degrees of freedom means, degrees of freedom is sum of the coordinates necessary to locate all the atoms of a molecule in space. So the total number of degrees of freedom in a molecule is 3n. 3n is the total number of molecules. Hence 3n degrees of freedom equal to translational plus rotational plus vibrational degrees of freedom. CO2 molecule is a linear molecule, hence translational degrees of freedom will be 3 and rotational degrees of freedom is 2, and we can calculate the vibrational degrees of freedom. Here it will be vibrational degrees of freedom equal to 3n minus 5. For CO2 it is a linear molecule, it will be 3 into 3. N is the number of atoms in a molecule. N is the number of atoms in a molecule. 3 into 3 minus 5 equal to 4. Hence vibrational degrees of freedom will be 4. The answer is 3 to 4. Answer will be 3 to 4. 3 translational, 3 degrees of freedom, rotational 2 and vibrational degrees of freedom are 4. Next question is, a compound shows a proton NMR peak at 240 Hz downfield from the TMS peak in a spectrometer operating at 60 MHz. What is the value of chemical shift in delta scale? If you want to calculate the chemical shift value in delta scale, you have to use this formula. The formula is delta ppm, means it is in the ppm. It is equal to observed shift in hertz divided by spectrometer frequency. Spectrometer frequency, that is, this will be in the megahertz. So here they have given the observed shift in hertz, that is 240, and spectrometer frequency is 60 megahertz. So if you divide 240 by 60, it will be 4. That is delta value. 4 ppm is the delta value. Hence option B is correct. Next question is, an organic compound having molecular formula C10H14 exhibited 2 singlets in Proton NMR and 3 signals in 13C NMR spectrum. The compound has the following structure. So here they have given the structure and given the data of C13 and Proton NMR. We have to find out the structure. The data is, in Proton NMR there are 2 singlets, and in C13 3 signals. Means there are 2 types of hydrogens are there in the molecule. Means 2 non-equivalent hydrogens, and there are 3 equivalent carbon atoms are there. Means 3 non-equivalent carbon atoms are there. Let's check the peaks for this compound. Here it is CS3, here also CS3, here also CS3, and here also CS3. these CS3 protons are, all these CS3 hydrogens are having same environment, so that all these hydrogens going to give the single peak. Here I'll write one first peak, and next to this carbon is not having hydrogens, hence this resonate as a singlet. These resonate as singlet. And another type of hydrogen is, this is another type of hydrogen. This hydrogen and this hydrogen are having same environment, and next carbon having no hydrogens, hence this is also resonate as singlet. In this molecule, under proton NMR, there are two peaks possible, both are singlets. And check for C13 NMR, 1 is same, all these are same, 1 2 3. So we can get three signals in C13. So this is the correct answer, because there are two types of hydrogens, both hydrogens give singlets, and there are three different types of carbons, so that we are going to get three signals in C13 NMR. We'll check for this compound. This hydrogen is different, these two are different, so it will be 2, this is 1, and this is 3, and this is 4. So in the proton NMR we can get 4 signals. In C13, 1 2 3 4 5 6 and 7. In proton it will be 4 and 7 will be in C13 NMR. Here 1, you can have this is a plane, this is exactly same as this, so that in proton NMR 1 2 3, 3 signals in proton NMR, and 1 2 3 4 5 signals in C13 NMR. Here you can have the plane here, 1 2 3 4 in C13 NMR, 1 2 3 in proton NMR. So I asked the 2 signals in proton NMR and 3 signals in C13, hence option A is correct. Next question is, what is the expected M+1 relative intensity in the mass spectrum of C13 compound? As we have discussed, M+1 peak in mass spectrum is due to the presence of isotopes, and the intensity of this M+1 isotopic peaks is directly connected to, or it is related to, the abundance of that isotope in nature. Here they are given the carbon atoms, carbon 12, and there are carbon C13. So the relative abundance is 100:1.1. This is the relative intensity of 12 carbon and 13 carbon atom. So we have to, so M+1 peak will be because of the presence of 13C carbon. The equation will be relative intensity of M+1 equal to 1.11 into number of carbon atoms, it is 60, so that the answer will be 66.6. This is the equation to calculate the relative intensity. Relative intensity of M+1 peak equal to 1.11 into 60. They have given only the presence of 60 carbon atoms, so that we are adding this. If they have given the another molecular formula containing hydrogen, sulfur, all those atoms, we have to add here, and we have to multiply the number of those atoms with their abundance, so that we are going to get the relative intensity of that molecule. Here they have given only the number of carbon atoms, and so that we are going to take only the abundance of carbon C13 isotope and into the number of carbon atoms. It will be 66.6, hence option C is correct. Next question is, the IR region corresponds to, here they are given the range, so you have to find out the IR region. Which is the IR region? Here I will show the IR spectra. This is the IR spectra. Here you can see that it will be around 667 per centimeter. This is the IR range. So the IR range is 667 to 4000 per centimeter. You can write 4000 to 667. This is the range of IR. 667 to 1500 is the fingerprint region. It is called as fingerprint region, and above 1500 up to 4000 per centimeter it will be functional group region. Total the IR region is 4000 to 667. In that 667 to 1500 is the fingerprint region, and above 1500 up to 4000 that region is called as functional group region. Here IR, they have asked IR region, hence 4000 to 667 is the IR region. If they asked only the functional group region, that will be 4000 to 1500. If they asked fingerprint region, that is 1500 to 667. Next question. In the broadband decoupled C13 NMR spectrum, the number of signals appearing for the bicycloacetones. In the past, here you can have the symmetry, means this part is same as this part, this carbon is same as this carbon is same as this carbon, and all these 4 carbons are same, these 2 carbon atoms are same, hence the chemically non-equivalent carbons are 1, 2 and 3. So we can get 3 signals for compound 1. Here this carbon, these 2 and these 2 all are same, having same chemical environment, so all these going to get only 1 signal. These 2 are different, hence this is going to get the second signal for these 2 carbon. These 2 are same, but these 2 are different from these other 6 carbon atoms, hence we are going to get second peak for this carbon, these and these carbon atoms. And here this is different, chemically different carbon, these 2 are same, these 2 are same, this one is same, these 2 are same, hence it is, we are going to get 5 signals in this molecule. Option, it will be, the answer will be 3, 2, 5. Option B is correct. For this we are going to get 3 signals, for this we are going to get 2, and for this we are going to get 5 signals. Next question is, oct4in shows C double bond C frequency in the range. They have asked the C double bond C frequency range in the octene, that is oct4in. Usually C double bond C frequency range in vibrational spectra is around 1650 per centimeter, but here they have given the molecule, that is oct4in. See, this is octene molecule, here you have to add CS3. This is oct4in molecule. This is symmetric molecule, this is same as this one, this half is same as this one. The selection rules for IR or the vibrational spectra is, there must be change in the dipole moment. If the molecule has or if the bond has to absorb the radiation, or it has to vibrate, it needs a change in dipole moment. If there is no change in dipole moment, it will not couple with the changing electromagnetic field, and it will not absorb radiation, and there will be no vibrations. But here in this case, there is a little amount of absorption or vibration will be takes place, and you are going to get the very, very weak peak at 1680 to 1660. Sometimes in the symmetric molecules there will be no peaks. In this case there will be very weak peak observed at 1680 to 1660. Hence option A is correct. In the broadband decoupled C13 NMR, the number of signals appearing for the molecule for the following bicyclic compounds respectively. Here we have to find the number of signals in the following compounds. This is a different, going to give the one signal, and these 2 are same, going to give the second signal. These carbon atoms 1, 2, 3, 4 all are same, having same chemical environment, all are going to give the single peak, that is 3 signals are observed for compound number 1. And here CH2, this carbon, these two and these two are all the 6 carbon atoms are having same chemical environment. All are going to give only one peak, and these two are different from the other 6 carbon atoms, and these are same, having same chemical environment, and these carbon is going to give second peak. And in this case, this carbon is different, this carbon is different, this is different than this is also different. The chemical environment is different for all the carbons. This is 6, this is 7, this is 8, and these two are also different because here this is attached to this carbon atom, but this is attached to these carbon atoms which is having methyl group. This is 9 and this is 10. All the carbons are different, hence it is going to give 10 signals, second going to give 2 signals, and first molecule going to give 3 signals, hence it will be 3 to 10. Option D is correct, it is 3 to 10. 3 signals, 2 signals and 10 signals. In the reaction, X exhibits the following spectral data. We have to find out the compound X from the following data. Here they are given the IR bands and information about the proton NMR. They are given 2 IR bands, that is 1745 and 1710. The range of carbonyl vibrational frequency is 1680 to 1810. So here they have given 2 bands which are in between in the 1680 to 1800. So both the vibrations are due to carbonyl. Check the molecule having carbonyls. These two, A and B, having carbonyls. There are 2 carbonyls. One is ester and another is ketone. Here also ester and ketone. Here only ester carbonyls are there. And then in the proton NMR, 1.28 3H, they have given 1.28 3 hydrogens triplet, 2.21 3 hydrogens singlet, 3.24 2 hydrogens singlet, 4.2 2 hydrogens quadrate. Just check the coupling and the NMR bands of this compound. This shows 3H singlet, this shows 2H singlet, this shows 2H quadrate, because this carbon is having 3 carbon atoms, n plus 1, that will be 4 means 4, because of that it is quadrate. This is 3H triplet. And next one is this one. This is 3H triplet, 2H quadrate, 2H singlet, 3H singlet. But we have discussed, when you have the methox group, the delta value will be 3.8 to 3.9. Here we don't have 3.9 delta value, that is for CH3. Hence this molecule is not the correct one. Here also one methox, here there are 2 methoxy groups, but as per the given data there is no peak delta value at 3.9, hence this is also not the correct answer. Here also we have methoxy group, this is not the correct answer. Check this value with this value with the given value. 3H singlet at 2.21, 2H singlet at 3.24, and 3H triplet. This is 3H triplet at 1.28, 2H quadrate at 4.2. Hence option A is correct. Here this is 3H singlet, 2H singlet, 2H quadrate and 3H triplet. Hence option A is correct. Next question is, match the following In the list A, they have given the groups, and list B, they have given the vibrational wave numbers. You have to match the groups with their respective wave numbers. CH, for CH, there are three types of CH, sp2, sp3 and spCH. So here they have given the CH. We have got to consider it as sp3CH. sp3CH vibrate at 2900, around 2900. sp2 vibrate at 3100. spCH vibrate at 3300. And here I'll write the sum of the groups and their vibrational frequencies. OH vibrate at in the range 3300 to 3600, but there are two types of OH vibrations, 3300 to 3450. It will be hydrogen bonded OH, and around 3600 it will be a free OH. And NH is also vibrate in the range 3300 to 3400. Important group is carbonyl group. Carbonyl group vibrate in the range 1680 to 1810. The standard carbonyl vibrational frequency for ketone is 1715. Here CH is 2900, around 2900. Here they have given 2850 to 2960. Hence one is D. OH is around 3590 to 3650. It is C. When it is hydrogen bonded, it is broad and it will absorb at 3300 to 3400. When it is free, it will be sharp and it is around, it absorbed at 3600. Carbon vibrational frequency range of this is 1640 to 1780. There is slight changes in the values. Carbon vibrational frequency is 1640 to 1780, and nitro will be 1350 to 1420. This is B. Hence DCAB. DCAB. Hence option A is correct. That is DCAB. This is different compounds having this different functional group having carbonyl. Highest is for anhydride, it is vibrate at 1810. Next acid chloride, it is 1800. Anhydride symmetric, it is 1760. Asymmetric vibrate higher than the symmetric. Here the anhydride asymmetric vibrate at 1810 and symmetric vibrate at 1760. Ester vibrate around 1735. Aldehyde vibrate at around 1725. Ketone gives the standard carbon vibration frequency, that is vibrate at 1715. Carboxylic acid vibrate at 1710. Amide vibrate at 1690. You should remember these values. Next question is asymmetric stretching vibration of CO2. They have given four options: Raman inactive, IR active, Raman active, IR active, Raman active, IR inactive, and both Raman and IR are inactive. To solve this question, we should know the selection rules for IR and Raman frequencies spectroscopy. The selection rule for IR is there should be change in dipole moment. There should be change in dipole moment. And for Raman, there should be change in polarizability. If there is change in dipole moment, then only the molecule is IR active. As we have discussed in the oct-4 both are symmetric. Both the parts are symmetric around the double bond. Hence, that is not IR active actually, because there is no change in dipole moment. And when it comes for Raman, there should be change in polarizability. Here I will give an example of CO2. This is CO2 molecule. This is symmetric stretching. This when the oxygen goes away, when both the oxygens go away from carbon, this is symmetric stretching. When one comes nearer to carbon, another goes away from oxygen, it is asymmetric stretching. When it's symmetric stretching, the dipole moment of this CO and this CO cancel each other, hence there is no change in dipole moment. If there is no change in dipole moment, then that molecule is IR inactive. Here it is IR inactive. But it is Raman active because there will be change in polarizability. Hence it is this touching frequency of CO2 is IR active, Raman active, IR inactive. In asymmetric touching frequency, there will be change in dipole moment because one oxygen comes nearer to carbon, another goes away from carbon. Because of that, there is a change in dipole moment, hence it is IR active, and there is no change in polarizability, hence it is Raman inactive. Symmetric is Raman active, IR inactive. Asymmetric is Raman inactive, IR active. And the third one is, this is bending. Bending is Raman inactive, but it is IR active. Here also there is no change in polarizability, hence it is Raman inactive. There will be change in dipole moment, hence the bending vibration is IR active. Here they have asked the asymmetric stretching. In the asymmetric stretching, there will be change in dipole moment, hence IR active will be there, and Raman, there is no change in polarizability, hence Raman inactive. The option A is correct, that is Raman inactive, IR active. Raman inactive and IR active for the asymmetric stretching of vibrations of CO2. Same question was appeared in the next question paper. Oct 4 shows C double bonds frequency in the range. This is very weak band at 1680 to 1600 because of there is no change in the dipole moment, hence it is weak vibration takes place, and we are going to get a weak band. Option B is correct. Okay, thank you.